Hello everyone, welcome back to my Continuum mechanics lectures. So today we will look at some problems related to tensor calculus. So first of all, let's discuss the identity which we had mentioned in the lectures, which we had said that we will look at in the problem solving session. That is divergence of A transpose U was U dot divergence A plus trace of A transpose. So this is gradient of U, or this can be written as A dot del U. So we know that, so let's do it using the initial notation. Let's write A as Aij, Ei dyadic Ej, U as Uk Ek. So A transpose U is Aji Uk Ei dyadic Ej Ek, which is Aji Uk delta Jk Ei, and this is nothing but Ki Aki Uk Ei. So this is a vector with the free index. So sorry, there is no free index. Free index is with the component AKI UK. So divergence of A transpose U is nothing but AKI UK comma I. So using the product rule, so a good discussion on the product rule and the chain rule is given in Gertin in the second chapter, which is, relates to tensor analysis. You should look that up. So using the product rule, this is AKI comma I UK plus AKI U K comma I. So what is AKI comma I? This is nothing but divergence of A, and AKI, so K is the free index in this quantity, and here also it's K. So this is the dot product plus, and what is this? This is a tensor K AKI, and this is also a tensor U K comma I. So this is A dot gradient of U, since we have proved this identity. Next, we will look at two important identities related to the divergence and curl. So the first of them, sorry for the little delay. So let's say phi and v are of class C2. What does class C2 mean? That they are twice differentiable, at least twice differentiable, that they can be differentiated at least two times. So phi is a scalar field and v is a vector field. So the first of them is that curl of del phi is 0. So you can an identity which another definition of curl other than what we have seen before is also that curl of a vector v is nothing but the axial vector of the skew symmetric part of the gradient of v. For A belongs to E3 is a constant unit vector, is an arbitrary constant unit vector, constant vector. This can be easily checked using initial notation. So when v is gradient of phi, we have gradient of phi minus gradient of phi transpose acting on A is equal to curl of gradient of phi cross with A. Now this can be checked that what is gradient of phi? This is phi comma ij, and gradient of phi transpose is phi comma ji. So as phi is of class C2, this implies that phi comma ij is equal to phi comma ji. That is gradient of phi is symmetric. Therefore, this quantity is 0. There is zero tensor. Therefore, this implies that curl of del phi is 0. This is 0 because A is an arbitrary vector. So for all A, curl of del phi cross A is 0, which implies that a gradient curl of a gradient of a function is always 0. The next we will see that divergence of curl of a vector v is 0. So curl of v in initial notation is eijk vk comma j ei. Divergence of curl of v is eijk vk comma j comma I. This is nothing but eijk vk comma ji. So this can be, so using the permutation symbol, this can be written as 3 comma 21 plus v1 comma 32 plus v2 comma 13 minus v3 comma 12 plus v2 comma 31 and v1 comma 23. So again, as v is C2, Vijk is equal to Vikj. The order of the differentials do not matter. Therefore, This cancels with this cancels with this, and this cancels with this. Therefore, divergence of curl of V is 0. Next, we will have a look at this problem. The problem number 2, where consider a function fr theta phi of spherical coordinates. So we had done Cartesian coordinates, we had done gradients in Cartesian coordinates and polar coordinates. So this is the same thing in spherical coordinates. We have to find the gradient of a scalar function phi with respect to spherical coordinates. So r is mod x, the radius, theta belongs from 0 to 2 pi is the azimuth, and phi belongs to minus pi by 2 to pi by 2 is the elevation angle mentioned from the equatorial plane. So let us draw a diagram here. So this is a point x, this is the vector x from reference position 0, this is the E1, E2 plane, and this is E3. So what r theta phi are? That the projection of x on the E1, E2 plane. This is the angle theta. Mod of x is equal to, this is small r, and the angle which this vector makes with the equatorial plane, which is the E1, E2 plane, is phi. So, let this uh, vector, the unit vector along this direction in the equatorial plane, be er theta. So perpendicular to this would be e theta theta, and this perpendicular to x along the direction of phi is E phi. So the vectors are given here. Position is described by the function x is equal to ri as a function of theta and phi. So x is r I theta phi. I is equal to cos phi er theta plus sin phi e3, cos phi er theta plus sin phi e3. Er theta is equal to cos theta e1 plus sin theta e2. E1, E2, E3 is a fixed orthonormal basis. Er theta is cos theta e1 plus sin theta e2. So again, as we have seen before, e theta theta is minus sin theta e1 plus cos theta e2 is equal to d of er theta upon d theta. Also, e phi is given to be I cross e theta. So e phi is I cross e theta, which is nothing but minus sin phi cos theta e1 in terms of the fixed orthonormal basis minus sin phi sin theta e2 plus cos phi e3. Now let us look at what the question is. So use the expression df is equal to del f dot dx. Find the components of del f in terms of the partial derivatives of f with respect to the orthonormal basis I, e theta and e phi. So I, e theta and e phi also form an orthonormal basis. So let's check it out. So df is given as del f dot dx. So df can be written as f is a function of r, theta and phi. This is del f by del r dr plus del f by del theta d theta plus del f by del phi d phi. Now what is dx? Dx is the expression of x is given that it is r I theta phi. So this is dr I theta phi plus r del I by del theta d theta plus r del I by del phi d phi. Del I by del theta is so I is del y del theta of cos phi er theta plus sin phi E3 cos phi er theta plus sin phi E3. This is nothing but cos phi er dash theta. Er dash is d by d theta, which is cos phi e theta, and del I by del phi is del by del phi of cos phi er theta plus sin phi e3. This is minus sin phi er theta plus sin phi, sorry, this is cos phi, derivative of sin is cos phi e3. So if we look at the expression of e phi, this sin phi and this sin phi can be taken to be common. So this becomes minus sin phi into cos theta e1 plus sin theta e2. Cos theta e1 plus sin theta e2 is nothing else than er theta. So e phi is minus sin phi er plus cos phi e3, which is what we have obtained here. So this quantity is equal to e phi. Therefore dx becomes dri plus rd theta cos phi e theta plus r e phi d phi. Therefore, what would be dr? Dr is nothing but dx dot I, because taking the dot product of with I renders this term and this term to be 0. E theta dot I is 0 and e phi dot I is 0 because they are they form an orthonormal basis. Similarly, d theta is 1 by r cos phi dx dot e theta, and d phi is 1 by r dx dot e phi. So using this in the expression of df, this is del f by del r dx dot I plus del f by del theta dx dot e theta by r cos phi plus del f by del phi dx dot e phi r. This is equal to gradient of f dot dx. So what does the gradient of f become? So taking dx out to be common, we have gradient of f to be del f by del r I plus del f by del theta e theta by r cos phi plus 1 by r del f by del phi. So this is the gradient of f in spherical coordinates. So this is the real power of that technique which we have discussed. So you can obtain the gradient of any function, whether it be scalar, or we can do the same for a vector valued function. You can obtain the gradient very easily in any coordinate system of our choice. Sorry, there's one E5 missing. Yeah, that should be E5. Next, let us look at question number 4. So for two vector fields UV, show that first divergence of U cross V is V dot curl of U minus U dot curl of V. Let's look at the first one. Divergence of U cross V. This can be written to be as U cross V is E K I J U I V J E K. Curl of U cross V is E K I J U I V J E K, and divergence of this would be differentiation with respect to K, xk. So using the product rule, Ekj Kij can be taken outside. U I comma K Vj plus E Kij U I Vj comma K. So this can be written as Vj E Kij Ui comma K minus of Ui E Ikj Vj comma K. We have just inverted I and K indices I and K, which gives us a negative sign. So this can be seen that here the only free index is J, and here the only free index is I, and this is nothing but curl of V, and this is nothing but curl of U. So this becomes V dot curl of U minus U dot curl of V. The second part of this question is divergence of U dyadic V, that is divergence of a dyadic product, is nothing other than gradient of U acting on V plus U into divergence of V. So let us look at this also. This is divergence of U dyadic V. So we'll take a dot product according to our definition of divergence as we had discussed in the lectures. We'll take a dot product with an arbitrary vector A which is constant. This is fixed. So this becomes divergence of A transpose A, so which is V dyadic U acting on A. This is divergence of U dot A V. This is equal to, so it can be shown using addition notation easily, that this is nothing but U dot A divergence V plus V dotted with gradient of this dot product U dot A. So this becomes U dot A divergence V plus V dot, this A is a constant vector. This can again be shown using the indicial notation. that this is nothing but gradient of u transpose acting on A. So gradient of u, this can be taken to be u divergence v plus gradient of u acting on v. You have taken the transpose on this side of the dot product dotted with A. Now as A is arbitrary, divergence of u diatic v becomes u divergence v plus gradient of u acting on v, which was our identity. Next we will look at some problems regarding the various integral theorems which we have seen before. So let me just take a moment. So v, w are continuously differentiable vector fields over a region omega, which is a subset of three-dimensional Euclidean space with boundary del omega. And A is the same, but it is a tensor field. So it is also a continuously differentiable tensor field over a region omega, which is a subset of three-dimensional Euclidean space with boundary del omega. Del omega has an unit outward normal n. The first identity which we want to show is that del omega integral over area integral over del omega v diadic n is gradient of v dv over omega. So taking as these are tensors, we take an arbitrary vector A which is fixed belonging to E3, and we apply these tensors on both sides to A. So that is del omega v diatic n A dA is equal to del v A dv. So working on the left hand side, which was V diadic N acting on A dA over del omega. This is N dot A V dA acting on omega. This can be written to be E dot N. Dot product is commutative, so dA del omega. This then becomes V diadic A acting on N dA. So using the divergence theorem, this is divergence of V diadic A. This now becomes a volume integral on omega. Now divergence of V diadic A, we have just seen, is nothing but V divergence A plus gradient of V acting on A dV integral omega. Now as A is a fixed vector, this is 0. Therefore, the left hand side becomes del V acting on A dV. Now the right hand side is also, this is equal to the right hand side. Now as A is arbitrary, integral del omega, what we started with, V diadic N dA is gradient of V dV over V. The next identity we will show is del omega V diadic A acting on N dA is V diadic divergence A plus del V acting on A transpose dV. Again, taking an arbitrary vector, constant vector, a fixed vector, A, and applying the tensor on both sides to A, we have del omega V diadic AN acting on A dA is equal to V diadic divergence of A plus gradient of V acting on E transpose acting on A dV. Let's work on the left hand side again. So this is V diadic AN A dA del omega. This becomes V AN dotted with A dA, which is N dot A transpose A V dA. This can be written as by taking the A transpose A dot N on V. This can be written as V diadic A transpose A N dA. Now, using the divergence theorem, this becomes divergence of V diadic A transpose A volume integral over omega. Now opening this up using what we have proved before, this becomes V divergence A transpose A plus del V acting on A transpose A dV. The divergence of A transpose A, with A being a fixed vector, from the definition of divergence of a tensor, we have nothing but V A dot divergence of A plus del V A transpose A. Now this can be written as V dyadic divergence of A acting on A. Therefore, the whole thing becomes V dyadic divergence of A plus del V acting on A transpose on A dV. And this is same as the right hand side. This is same as the right hand side. And as A is arbitrary, the LHS is equal to RHS. The last problem which we'll look at for today is the third identity which we want to prove, is del omega V multiplied by W dot N dA is equal to V divergence W plus del V W dV. So again, working on the left hand side, we have del omega V W dot N dA. This can be written as del omega V diadic W acting on N dV. This is dA. Using the divergence theorem, this can be written as divergence V diadic W dV on omega, volume integral on omega. And as we have seen already before, this is nothing but V divergence W plus del V acting on W. Hence, LHS is equal to RHS. So that's all for this problem solving session. So next we will start with kinematics, or the study of motion. Thank you.